Alright, so the next lesson for Math 20-2 in angles and triangles, the sine law. So in the last one we proved the sine law, that it's going to be true in every case. So now we're going to look at kind of some examples of how we're going to see it. So when we proved it, we just kind of proved a portion of it. We proved, this portion of it, but we could go through the same process and prove that it's actually true for any of those ratios between a side length and the sine of the angle that's opposite from it. So we actually we can write it the full way that side length A divided by the sine length of A is equal to side length B divided by the sine of B equals side length C divided by the sine of C. And so again, first what we did is we drew an example and saw that it might be true, and then we proved that it's going to be true in every case. So on your, I know you guys aren't really using your formula sheets right now, but on your formula, I don't know why, well, there we go. Formula sheet, I think it only has it one of these ways, but you can use both of them. So we can either have side lengths on the top, like in this one, or we can have the sine of the angle on the top. And so this one is useful or easier. Both are fine, it doesn't really matter. But this is easier or more useful for determining a side length. And this one, so writing it with the sine of the angle on the top, is easier or more useful for determining an unknown angle. And so you're only ever going to use like two portions of it. You're not going to use all three. But know that it's also the sine of m divided by side length m equals the sine of n divided by side length n. You don't have to use a, b, and c. If you have a triangle that maybe doesn't have a, b, and c and you need to relabel it, that's a-okay, but know that it doesn't have to be a, b, and c just as long as you're using the angle that's opposite of the side length. And so sometimes if you don't have a labeled triangle, you need to do that so that you keep all of those numbers and sides straight. So let's look at the question. There we go. Okay, so again, use either form. I always look at the question and figure out, am I looking for side length or am I looking for an angle? And then I choose accordingly. So it says a triangle has angles measuring 80 degrees and 55 degrees. The side opposite the 80-degree angle is 12 meters in length. Determine the length of the side opposite the 55-degree angle to the nearest tenth of a meter. So this is actually kind of a hard question in that you don't have the triangle drawn for you. So sometimes I'm going to give you a triangle and it should be pretty straightforward, like you need to figure out this side length or something like that. This one's actually a little bit more complex in that you're just given information and you kind of need to draw it out. And now don't start panicking and say, oh, I don't have a protractor with me or anything like that. You don't need it. So you just draw kind of to the best of your ability for this one. But again, I would say drawing the triangle is actually important for this one. So look. So a triangle has the angles measuring 80 degrees and 55. So we know that that looks pretty close to 90 degrees, right? So I'll just go a little bit more. I'm going to go way long, just in case. And then 55. So that's probably 45-ish. So I'll just go there-ish. Again, does not have to be perfect at all. Sorry, I have this tail and I remember that it won't let me erase it. So we'll just have to kind of tolerate that. So now, just labeling the triangle with the information from the question. And again, it doesn't have to be perfect. I can see that this angle probably is not exactly 80. This definitely is not 55, but you know what? We'll get by. This is enough for us. So, like we said, this is 80, and this was about 55 degrees. And the side opposite the 80-degree angle is 12 meters in length. So again, opposite right here. Um, so, sorry. Determine the length of the side opposite the 55-degree angle. So this is kind of our question mark, is the one that's across from it. Just as a note, so we could figure out this angle, right? We know angles in a triangle will add up to 180 degrees. So that technically, if we needed it, would be 45 degrees. But in the context of this question, we don't actually need to do that particular step. But just if we did, oops, erase. So determine the length of the side opposite the 55-degree angle, the nearest tenth of a meter. So I'm going to label my triangle just so that I'm keeping things straight. So I'm going to put an A up here and a little a here. I'm going to put a B here and a little b here. And I could also do, so that being angle C, that being side length C. Again, we don't need it right now. So you're probably kind of wondering, well, why do I need to do this? I already know how to solve for things like this from primary trig ratios. But what you see, this is not a right angle, or not a right angle triangle. So we can't use our primary trig ratios of the sine of an angle is equal to the opposite over hypotenuse, because we don't actually have a right angle anywhere, right? We have 80, 55, and 45. So not a right angle triangle, need to use the sine law. And so just thinking about this, so it's saying it's determining side length. So I know up above we said this is kind of the form if we're determining a side length. That's the form that we want. And again, we don't need to deal with C. It's just asking us for side length B. So we're just going to use the first two portions of that. So A divided by the sine of angle A is equal to B divided by the sine of angle B. And again, we're looking for side length B. Sorry, I can full screen. We are looking for, no, so we're looking to solve for this. Looking to solve for side length B. So I know if I rearrange that formula, I would need to multiply by the sine of angle B. So multiply both sides by the sine of B. So now I have the sine of B multiplied by A divided by the sine of A is equal to side length B. And so some of you might see at this point and be like, that looks like a cross multiply and divide situation. All the power to you if that's how you want to visualize it. We're doing the same step here by rearranging the equation. So don't think that you're doing something wrong if you're thinking cross multiply and divide, but just don't mess up cross multiply and divide, right? So cross multiply, so A times the sine of B, which is what we have here, and then the divide by the sine of A. So now I can substitute in the known values. So the sine of angle B is 55 degrees, multiplied by side length A, which was 12 meters. I don't need units. What am I doing? Divided by the sine of angle A. And angle A was equal to 80 degrees. So once you punch that all in to the calculator, I think it comes out to 9.98 meters. It says to the nearest tenth of a meter. But the number I would be dropping would round up, so I guess it'd be 10.0 meters. And just, I know our diagram wasn't super accurate, but just looking if that makes sense. Yeah, that probably makes sense. If we had got something like 15,000 meters, well, that doesn't make sense, right? We have a side length of 12. Why would the other side length be 15,000 meters? Or if we got 0.4 meters, probably not right either. So thinking about whether your answer does actually make sense. 10 meters makes sense in the context of the question. Sorry, I hope you got everything down you needed there. All right, so one more question. Again, there's going to be lots of examples of ones that are similar where you don't have to draw the triangle out and you're just given enough information. So you just need to be able to apply whichever form of the formula. So again, useful for side lengths. This is useful for angles, and we'll see. We're going to use that in the next one. So I'll show you how it's done. So Toby uses chains attached to hooks on the ceiling and a winch to lift engines at his father's garage. The chains, the winch, and the ceiling are arranged as shown. Toby solved the triangle using the sine law to determine the angle that each chain makes with the ceiling to the nearest degree. He claims that theta is equal to 40 degrees and alpha is equal to 54 degrees. Is he correct? Explain and make any necessary corrections. Well, this would just be a ridiculous question if he was correct. Of course, Toby's wrong. What are you doing, Toby? So, this is the diagram. I don't know why Toby's doing this, but he's definitely wrong. So he's proposing, that doesn't mean that these labels are right, but I was just kind of writing it on. He's saying this angle is 40 degrees and this angle is 54 degrees. All right, I can get behind that in that 86 plus 54 plus 40, that adds up to 180. So they could be right, but the way that I can actually tell that Toby is wrong, you wouldn't want to, grab out a protractor and be like, he's wrong because I measured it, because sometimes the diagrams are way off. But the way that we can tell without having to measure it is, whoa, what? Um, because if you look at the side lengths, sorry, I guess I could have left this on. So he said 40 and he said 54. So he's saying angle alpha here is 54 and theta is 40. If we look at the side lengths that are across from them, the bigger the angle, the longer the side length should be. So 54 is across from the 1.9, 40 is across from the 2.2. So we know that he is wrong because this is the bigger angle, so it shouldn't be the shorter side length. So we know he's wrong because the longer side length should be across from the bigger angle. Sorry, I just heard a weird noise. So we know he's wrong. So let's erase his guesstimates and let's make all the necessary corrections. You probably wouldn't also just want to be like, well, I guess then this is 40 and this is 54. He must have just wrote them in the wrong spots. We want to actually calculate out what they would be. So we're going to be looking for an angle. So yes, they have the angles labeled as alpha and omega here. I'm going to just do the ABC thing. So I'm going to label my triangle. This is angle A. This is side length A. That's confusing because this is A, so I'm just going to overwrite it and be like, this is angle B, this is side length B, and this is angle C, this is side length C. So let's just get rid of these for right now, just because that could get confusing. So I've relabeled my triangle ABC. You could leave them as alpha and omega, all the power to you, but I'm going to do this. So since we're looking for an angle, I'm going to, oops, I was pressing erase, use it in this form. So where we have our angles on the top. So I think I'm going to deal with trying to find out the measure at angle B right now. So I'm going to use, since I have information about angle A and side length A, I can use that piece of information, and I have side length B, so from that I'll be able to figure out angle B. Mm. So I have the ability to use the sine law, and again, we're going to use it in the form, the sine of angle A divided by side length A is equal to the sine of angle B divided by the sine O divided by side B. So I know that I'm trying to find information related to angle B. So what I'm going to do first is solve for the sine of B. That's not quite all the way. I'm going to multiply both sides by lowercase b. So B multiplied by the sine of angle A divided by A equals the sine of B. So this is, we're not quite done when we get to this point, and you will recognize that we're not done just based on how the answer comes out. So side length B, if I go back up, side length B was 1.9 meters. Side length A was 2.8, and angle A was 86. So 1.9 multiplied by the sine of 86 divided by 2.8. What we get there is 0.6769. I think there's more numbers. Don't just round this to 0.7. Keep 4 decimal places when we're dealing with angle stuff. If you round it too early, you're going to end up with an answer that's a wild amount off. So 0.6769 is equal to the sine of angle B. So again, we're looking for angle B, but what we have right now is the sine of angle B. So you need to use, in order to solve for B, you need to use your inverse sines. That's sine negative 1, 0.6769 will get us our angle. So hopefully you didn't get to this point and be like, yeah, that measure at angle B is 0.7 degrees. That's like, that's way more than 0.7 degrees, but I can't draw them close enough together. So we know it's not 0.7 degrees. So you need to use your inverse sine. So when you punch that through, again, keep more decimal places if you want. We get 42.60 degrees is equal to angle B. You might, I think I rounded this to 43 degrees is equal to angle B. So now if I go back up, I get angle B. Again, that was representing our, what we called alpha, or what Toby had called alpha. So this is 43 degrees. And so we could find angle C by using the sine law again. We know I'm lazy. So we could use the sine law. So we could do um, the sine of angle C over side length C equals the sine of, we could either use A or B there now. I'd probably use your original. So we could do it this way. Good practice. We're learning the sine law, but I'm lazy. So I know um, angle A plus angle B plus angle C needs to be equal to 180 degrees. Because they are all interior angles of a triangle, so we know they would add to 180 degrees. So what I could do, I know angle A is 86 degrees. We just calculated angle B. It's 43 degrees. So I could subtract 86 and 43 from both sides, and we could get angle C equal to 51 degrees. So back up. Oh, you probably run out of room by now. So this is 51 degrees. All right, so it's a word question. You might write, Toby is wrong. I was trying to think of, like, should I write ridiculous or something? Toby is wrong. So theta, which we labeled as C, is equal to, sorry, 51 degrees, and alpha, which we had labeled as B, was equal to 43 degrees. Get back to work. Toby. Um, okay, so that's all I have for the sine law. So you have some practice questions from page 138-ish. So page 138, questions 1 to 5, 6AB, 7, 8, 10, and 15 are looking at the sine law. So that's all for today. Have yourselves a good one, and we'll talk to you later.